All right, next lesson, we're going to talk about osmosis and osmotic pressure. So I'm going to give you a couple different definitions of osmosis. We'll start with the one that's in the notes. Osmosis is the movement of water across a semi-permeable membrane, meaning some sort of barrier that allows certain things to pass, such as solvent particles, and doesn't allow other things to pass, such as solute particles from a compartment. Now here's where it's different definition here than what you probably learned in biology. From a compartment of higher solvent concentration to a compartment of lower solvent concentration. So take a look on page 533. So the pink is the solution and you got pure solvent, that is the white, I guess we'll call that. And so the solvent just all by itself is going to want to move from, let me give you a different definition of osmosis. Osmosis is the diffusion of water from an area of higher solution from an area of low to high solution concentration. So in this case, the water, we'll say that the white is water, the pure solvent, moves, the net movement is from right to left. So it's moving into a solution of greater solution concentration. And so osmotic pressure, if we look in letter C, is the pressure that must be applied to prevent that net movement of solvent through that semi-permeable membrane. So that's what osmosis is, movement of a solvent from an area of lower solution concentration to higher solution concentration, or as the note says here, from higher solvent concentration to lower solvent concentration. So again, there's our definition of osmotic pressure as well. If you take a look at the top, also on the top of page 533 in the margin, figure 21.9 has started with the bottom of the page. Same idea here. So we have sugar molecules, a solution of sugar water on the right and just pure water on the left. And so the water is going to want to move into the solution of sugar. So it shows arrows pointing both directions. There is a net movement of water both directions across the membrane, but water is going to move first into the sucrose or sugar solution. This is very important. If you take a look at the top of page 534, figure 2111, that should say 2111. It shows red blood cells and the movement of water either into or out of a red blood cell depending on the environment it's in. So if you put a red blood cell in a solution of higher concentration, water is going to leave. So that's a letter C. Water is going to leave the red blood cell and it's going to shrivel. The opposite's also true. If you put a red blood cell, say, in just pure water, the water is going to diffuse into the red blood cell and cause it to burst. So it's important that to prevent too much movement into or out of a red blood cell, that the red blood cells are in the concentration of stuff inside the red blood cell is comparable to the concentration of the stuff outside the red blood cell. So there's really no net movement of water into or out of the red blood cell. All right, so let's take a look at some calculations involving osmotic pressure. Here is the equation we're going to use, where pi is the osmotic pressure in atmospheres or kilopascals or torr. Depends on something we'll see in a second. Big M here is our molarity, molar concentration. So concentration is directly related to osmotic pressure. So the greater the solution concentration, the greater the osmotic pressure. R is our ideal gas constant. I'm not sure why I've given you, 5 significant figures there. 0.0821 will probably be okay. So if you use 0.0821, that means then the osmotic pressure will be calculated in atmospheres. Of course, if you use 8.314 liter kilopascal per mole Kelvin, then that means the osmotic pressure will be in kilopascals, and 62.4 liter torr per mole Kelvin means that the osmotic pressure will be calculated in torr. And we also see that temperature is directly related to osmotic pressure. So the higher the temperature of the solution, the faster the particles are moving, the more they are going to diffuse through that semi-permeable membrane. Therefore, the higher the osmotic pressure. All right, let's take a look at some examples applying this formula. It says what osmotic pressure, let's go in kilopascals, is exerted by 1.82 molar solution at 18 degrees Celsius. All right, so let's start off with our equation. So we're looking for, if we go back here, we're looking for pi this time. So we'll just plug in our values. So concentration is 1.82 molar, which is moles per liter. If you're keeping track of units, in fact, we may want to keep track of units just on this first one. I'm going to put it in moles per liter just to show you what happens with the units. Ideal gas constant, we want the osmotic pressure in kilopascals, so we're going to use the value that has kilopascals in it. And then multiply that by our Kelvin temperature, which is 291 Kelvin. So let's take a look at the units. Kelvin cancels, moles cancel, liters cancel, so we're left with kilopascals. Go ahead and pause the video and see what you get. All right, so we should get, I'm going to put this in scientific notation. So we should get about 4,400 kilopascals. Now we want 3 significant figures. And so the only way to express 4,400 in 3 sig figs is to put that in scientific notation. So that's why I've done that there. All right, number 2. The average osmotic pressure of blood is 780 kilopascals at 25 degrees Celsius. What concentration of glucose, C6H12O6, in water will have the same osmotic pressure? So going back to our formula, this time we are looking for molarity. So we're going to rearrange the equation to solve for M. I think I'm going to let you do that on your own. Go ahead and pause the video and set that up. So here's our setup equation. M equals pi over RT. Plug in my values. So again, notice kilopascals cancels, Kelvin cancels, and we're left with 1 over liter per mole. If we flip that and put on the top, we end up with moles per liter or molar. So in our original value here for pressure, osmotic pressure, we're giving it to 2 sig figs. There's no decimal after the 0, so that 0 is not significant. And so our answer then will be expressed to 2 significant figures, hence the 0.31 molar. All right, let's try a different one. The osmotic pressure of a hemoglobin solution is 0.40 kilopascals at 25 degrees Celsius. The solution contains 0.300 grams of hemoglobin in 30.0 cubic centimeters or milliliters of solution. Find the molecular mass or molar mass of the hemoglobin. So again, we have a situation where we're trying to find molar mass. So let's jump to the very end. We don't know the molar mass of hemoglobin, and so we're asked to find that. So we're going to take the mass of the hemoglobin, which is given to us in the problem, and divide it by moles. Okay, so kind of like what we did with boiling points and freezing point of solution, we can use colligative properties to determine the molar mass or molecular mass of the solute. So instead of given the boiling point or freezing point of a solution, we're given the osmotic pressure. So what are we going to use the osmotic pressure to find? So we know osmotic pressure. We always know R. We know the temperature, so let's use that to find molarity. So kind of like what we did with boiling point elevation and freezing point depression, where we used those formulas to find molality. This time we're going to find molarity. So let's go ahead and set that up. So again, we have pi over RT. Once again, our pressure is in kilopascals, so we want to use the R that has kilopascals in it. Won't always be that way, but just be careful. So that will give us our molarity. Go ahead and pause the video and get that number, please. All right, so not a very high osmotic pressure, so we should expect a pretty low concentration, and that's exactly what we have. 1.6 times 10 to the negative fourth molar is the concentration of the solution. So keep in mind, we still need to find moles. So we know the molarity of the solution. How can we find moles of solutes? Well, what else do we know about the solution? We know its volume. So think about the formula for molarity. If you know the molarity of a solution and you know the volume of the solution in liters, then you can determine moles of the solute. So let's go ahead and do that. I'm going to just do that down here just as a separate step. So we're going to take the concentration of the solution and multiply it by the volume in liters. So 30.0 cubic centimeters is the same thing as 30.0 milliliters. Be careful with your conversion. To convert from milliliters to liters, you're going to divide by 1,000. And again, be careful of your significant figures. 30.0, that's 3 sig figs. When we convert to liters, you still have to have 3 sig figs. Once again, go ahead and pause the video and get that number. So hopefully you got that value, 4.8 times 10 to the negative fifth moles of hemoglobin. And so we're going to take that number and put it in here for moles. So let me reset this up here. Actually, I can just do it down here, is fine. So we have 0.300 grams of hemoglobin. And we have 4.8 times 10 to the negative fifth moles of hemoglobin. Let's put this back up here since we need that. Go ahead and pause the video and see what you get. I mean, look at the number of moles real quick. That's really small. You're dividing something by a really small number. Don't be surprised with your answer. Go ahead and pause and punch that up now. So once again, we want 2 significant figures in our answer, all because of our 0.40 kilopascals. And so when we get our molar mass, we get about 62,000, 6.2 times 10 to the fourth grams per mole, or 62,000 AMU technically. If we're answering the question as asked, we're trying to find molecular mass. So 62,000 AMU. All right, let's try another one. Calculate the osmotic pressure at a temperature of 25 degrees Celsius of a solution with a concentration of 0.490 molar. Now, it doesn't specify the unit, so let's do this. Calculate the osmotic pressure in anything besides kilopascals. I'll let you decide how you want to do that. Go ahead and pause the video and set that up. All right, so I decided to use 0.0821 for R. That means the pressure I calculate then will be in atmospheres. So 12.0 atmospheres. If we convert that to torr, that would be about 9,110 torr. All right, that concludes this lesson. Next time we'll wrap it up with distillation. Thanks for watching.